Alright, so this recording is about the chapter on rolling contact bearings, chapter 14. Bearings are used to support shafts in rotation. There are applications where bearings are used with other than what appear to be precisely shafts. There are alternatives to using rolling element bearing, also called and these are the historically the first that have been used, that is plain surface bearings. This is an example of a bearing, open bearing, as you can see, used in old rail cars or maybe locomotives. And you can see here the lubricant and the friction element. Okay, so the chapter presents the various type of bearings, and then calculations, methods of calculating for desired life of the bearings, and criteria of selecting them. The most common rolling element bearings are the deep groove bearings, also known as Conrad bearings, and they consist of an inner race and outer race rolling elements, that is balls, which are equally spaced and maintained at the desired equal distance by the cage or retainer. Okay, so clearly you're going to study the chapter, I'm sure. There are various designs of bearings. The deep groove single row, the Conrad bearing, is the most common one. But there are other designs you may not be familiar with. So here we have the deep row, double row deep groove bearing, and clearly with two rows of rolling elements, the load carrying capacity is increased. You'll see when it comes to the angular compliance, the slight angular misalignments between the two ends of the shaft, this will be a stiffer arrangement than the single groove or single row of ball bearings. The bearings with angular contact, on one hand you can separate them, that is the inner race and the outer race. Usually inner race is assembled with the shaft, outer race is on the housing, and they are used in pairs for that reason, and they have the ability to carry more thrust load than the standard Conrad bearings. You see them in several places on bicycles, the pedals, the wheel bearings, as well as the front wheel fork and handlebars. They are on a pair of this type of bearings, angular contact bearings. The cylindrical roller bearings clearly is even stiffer because of the geometry of the rolling elements to begin with, but they have higher load carrying capacity because of the type of contact. So instead of having point contact between the races and the rolling element, here the contact is it's a line. They don't have any thrust load carrying capacity. They can even be separate, the outer race from the inner race with the retainer, with the cage, and you sometimes see them used as a single bearing to allow for thermal expansion, because again the possibility of locating the rollers slightly as we look at this figure to the left or to the right of the outer race. A version of the cylindrical roller bearing are the needle bearings. And needle bearings are used when size is a limiting factor. For example, in universal joints, you see them on each of the forks. There's one of these needle bearings. You can see them here. They're the follower, cam follower, or in general when it's a small size compact arrangement is required. The designs could be where both an inner race, the rolling elements, and an outer race are provided. Sometimes you could see the inner race being actually part of the shaft, and the shaft is hardened to the necessary and finished to the necessary diameter. So there's again the bearing consists only of the outer race and the needles. And needles do not have a cage; they are just located, but there's no spacer between the individual needles. The spherical roller bearings, you see this design here. So your two, in this case, two rows of barrel type rolling elements, and the outer race is spherical to the inside in shape, and if there's any deflection of the shaft with a change of slope at the ends, the rollers can orient themselves at a desired angle relative to the outer race. Usually the inner race rotates with the shaft. The outer race is stationary, fixed to the housing of the equipment or on bearing blocks. Another type of bearings are the taper roller bearings, and they have the ability to support a significant amount of thrust force. They are always used in pair, and the arrangement is where the bearings are mirrored relative to each other, and mirror could be, if you look at this one here on figure 14.7, could be mirrored to the left or be mirrored to the right. If you look carefully, it's not the same thing. They can be separated. That is, the inner race with rolling elements and the cage can be separated from the outer race, and the designer should consider how to adjust and maintain the desired small clearance between the as the bearing gets put together. You see them with for sure on a vehicle, the differential is supported on a pair of this type of bearings, and elsewhere you can see them maybe on the like rear axles to support the wheel hubs themselves. It could be where we have the bevel pinion that meshes with the bevel gear inside the differential housing, and possibly elsewhere on an automobile. Like I said, so they are always used in pair. You will never see just one of them in use. Okay, there are other type of bearings, but here also listed there are the thrust bearings, capable of carrying axial loads only. and sometimes you see them used together with regular deep groove bearings to provide the necessary radial support, and then the thrust. So at the end, you see this type of bearing used. Think of a drill press. So as you load, as you drill, there's thrust load that's generated, and you'd expect to find one of these bearings at the end opposite to the chuck on a drill press, and likewise on a milling machine, and potentially on turning machines on lathes. Okay, pillow block bearing, mounted bearings. They come readily assembled, where you have the rolling elements, the race already mounted, rather the outer race already mounted on the block, and then the inner race, it may have set screws or a means to attach the inner race to the shaft. Some of them can be self-aligning, so similarly to spherical bearings, allows for the possibility of misalignment. So imagine you have two bearings, and they may have the base surface that are either offset and stay parallel, or they may be in misalignment both as angle and as and being in different planes. So serving the same purpose of spherical bearings. And I've seen these they are convenient to use. I've seen them. I've seen students using this type of pillow block bearings. There are other designs where they're flanged rather than being on a pad, including with means of tensioning belts, for example, that are carried on their sheaves or pulleys being carried by a shaft that attaches in this area. So you see the set screws that I mentioned not visible here. There are possibly other means, like I'm looking here, it looks like there is split bushing, and you can tighten it, you can clamp the shaft to it. Here you can use set screws to secure the shaft with the inner race. Okay. These are take-up frames that go in conjunction with the guiding grooves. Again, when you want to have the possibility of moving the bearing parallel to its own axis to, say, tension a belt, or could be a conveyor belt or a chain. In terms of the materials, bearing materials, there are alloyed steels. You can see the alloying elements in addition to carbon. There are high carbon steel for hardness. There are also alloying elements like chromium and manganese and silicon. So hardness is the main requirement, as well as stability. Over time, you don't want to have any phase change. Minute changes in dimension can occur with phase changes. Everybody knows of quenching, where we have phase change by rapid cooling, but phase change can occur over extended periods of time, and can be, the crystal system, if it's changing, it can happen with a volume change, and the bearing could seize because of that. So another requirement is contact stress, ability to cope with the contact stresses that occur under load, and wear resistance. Rolling elements, as well, the entire bearing could be made of materials other than of ceramics, for example. So these all would be non-conductive bearings. They are desired, even if only the rolling elements, they are desired when used with electric machines, because you can have here, I believe there was a so you're looking here at a let me make this smaller. So what appears to be an electric discharge, which damaged the bearing, maybe because of I know for a fact this was used with a wind turbine, so maybe a lightning caused this damage. But you can have in electric machines like generator and electric motors, you can have stray currents, and if the current is closing through the rolling element between the two races, you have sparks created, and the sparks damage the surface and could cause rapid wear of the bearing. This is how worn out bearings look like. You can see this is a localized wear. It's not going all the way around, but it could be, the damage to the rolling elements, pitting and spalling, and here the type of damage to the surface. So bearings don't last. Rolling element bearings don't last forever. That's a fact, and there are various mechanisms of failures of the races of the rolling elements. And again, when you have electric discharges, stray currents, you could prevent those from happening by using non-conductive, at least rolling elements, if not the full bearing. Okay. So there's bearing materials that are listed in this chapter with their properties. You can see it could be other than ceramic. The ceramics are they're stiffer materials, so you can look at modulus of elasticity. So this is common for steels, 30,000 KSI, but for ceramics it can go higher. Silicon carbide is almost more than double the stiffness. Okay. All right. Very important for design is this equation, the load-life relationship, and if you were to test a lot of bearings, of course it's not it's a statistical measure, but you see that for the same type of bearing, same bearing from the same manufacturer, if you load it at load P1, the corresponding life will be L1, and if you load the bearing at the different load P2, the life would be L2. The relationship between the two loads and two lives would follow this equation, with this exponent being either 3 for roll bearings or for ball bearings, or 3.33 for roller bearings. Okay. So very important finding, and this forms the basis for defining what are called dynamic load rating. So from manufacturers' catalogs, you would see, is there a way I can rotate this? Rotate view clockwise. Okay. So in this table here, you see a selection of bearings listed by their bearing number, and you can see the nominal size. And for the same, that is the bore size. So this and bearings, by the way, they are available in metric primarily. So even if the rest of the equipment has been designed in inches, the bearings very likely are millimeter size, and not that you couldn't find inch or bearings in inches, but they are metric. Anyway, so for the same bore size, they have 3 bearing numbers, And there are differences in size. So same bore diameter, but the outside diameter is increases from 26 to 35. So and then the width also goes from 8 millimeter to 11 millimeters. So between 6000 and 6300 series, you'd expect the third one, this one 6300, to be a higher load carrying, to have a higher load carrying capacity, just because of the size. It's increased. Rolling elements are bigger. Okay, and likewise, so as you move down the table, you can see for the same bore size, multiple series. Also listed here in this table, other than geometry, it's the bearing mass, recommendations to based on the fillet radii. So you see here there are fillet radii both the inner race as well as the outer race, and the recommendation in this table is about how small how more big the shoulder, or rather the transition between the where the step of the shaft is, was the bearing go, what should be the minimum shaft shoulder. If the radius is too big, then when you insert the bearing in place, I'll refer to this again. So if the radius is too generous, the bearing does not touch the shoulder, and it can can result in assembly errors, as well as the possibility of wedging the either the inner race or the outer race relative to that too generous fillet radius. But regarding the bearing life, you have here two figures. It's the static rating and dynamic rating, C0 and C. Okay, and as you can see, so we have the static load rating and dynamic load rating as numbers. And let me go back to the original view. So here's the various series size for the same bore diameter. You can see the heavy size, it's much bigger. Rolling element that is ball bigger, and this can carry much more load for the same life than this other one. Okay, so we have the dynamic load rating of a bearing, and the dynamic load rating is it's in the early equation, the first equation of the chapter. So would be imagine, say, P1 being replaced with C, dynamic load rating, and the corresponding life to the P that is C, dynamic load rating would be 1 million cycles or rotations. So to dynamic load rating corresponds L10, 1 million L10, 1 million revolutions to failure. Well, failure of what? I said that this is a statistical figure, and it's based on the probability of 50% of a lot of bearings, identical bearings, being loaded at that dynamic load rating haven't failed. So 50% of them having failed after 1 million cycles. So that's the dynamic. Am I saying the right thing? So if it's L50, okay. So if it's L50, 50% of them have failed. If it's L10, 10% of them have failed. Okay. So yeah, that will correspond to a reliability of 90%. L50 corresponds to a reliability of only 50%. Okay, so we have the early equation restated, and what you're seeing here is the number of cycles, design life in number of cycles, and the design load, and C, dynamic load rating, and 10 to the power 6, that's the life that's corresponding to dynamic load rating, 1 million. So you can have a problem. The problem stated as given the load and the bearing with dynamic load rating C. So load on the bearing given. Bearing is selected. We know the dynamic load rating. What would be the life? And you calculate design life. Or you can work with this other problem equation, which is restated of this one or the earlier one, when, where we have C going with L10. So here we have the load, the desired life, and we can calculate the desired dynamic load rating, and you need to select a bearing that has at least this much dynamic load rating. Okay. Oftentimes the life of the bearing is not given in cycle, but rather we're given RPM of the shaft and number of hours of operation per day, and number of days a week to be used. So this table here lists possible lives based on application. So for example, automotive. Okay, you can calculate. So if I have a vehicle that is traveling at an average speed of 60 miles per hour, and if it's if it's used 5,000 hours, so 5,000 hours times 60 miles per hour would correspond to 300,000 miles odometer reading. Again, it depends. For say it says aircraft engines, you have periodic inspection and engine rebuild, and they can afford to go with shorter design life. That means lighter weight, but requires more frequent diagnosis and preventive replacement of components. Okay. All right. So when it comes to bearing selection now, it could be the case where we have a combination of radial load that's primarily expected, but you can also have thrust load, and this could be the case of bearings mounted on shafts that carry helical gears, and by the mesh of a helical gear pair you also have thrust load generated, as well as bevel gears. So you have bevel gears in use, and their shafts are also subject to thrust load. Okay, let me take a break. All right, so when a bearing is loaded with other than just radial load, there are ways of combining the thrust load with the radial load and getting an equivalent radial load. Same happens if instead of the inner race, which is the most common arrangement, you have the outer race rotating, inner race being stationary. There is this factor V, rotation factor, that makes that correction. So if the outer race rotates, then the multiplier is 1.2, otherwise it's going to be 1. Okay, so Oftentimes you go through the process of selecting a bearing. Sometimes you have a given bearing that you adopt from other consideration. You want to know what would be the life of that bearing. Sometimes design goes this way, and from other considerations like size and the diameter of the shaft that has been already established based on strength calculations. Okay, so when we have both thrust load and radial load, we calculate the equivalent load by combining the thrust load and radial load using certain factors. One of them has already been introduced, so a rotation factor. If the outer race rotates, inner race is stationary, then the multiplier is 1.2, otherwise it's 1. And then we have the x and y factors, the radial and the thrust factors. And again, assuming that we have a bearing that we know, it's in an assembly, we know the thrust, we know the radial load, we can calculate these ratios, that is thrust load over radial load, and we compare it with this coefficient E, and if the ratio thrust over R is less than E, then we're essentially ignoring the second term. Otherwise, we do combine them. So, and then the corresponding radial factor that is going to be the same, 0.56, and it's only the thrust factor that is it changes. When selecting a bearing, the situation is a bit more ambiguous because we don't have the bearing known, and we don't know the static load rating, but we can assume, and this is a sample problem, you can assume an average value. Okay, so value between 1 and 2.3, average 1.5 for an initial guess, and then we refine it from there. But again, it's a matter of calculating the ratio T over R and compare it with this number E, and you either ignore, for when essentially the thrust load is relatively small, ignore that its effect, or you combine them based on this equation 14.5. Okay, we'll do some problems for this chapter. You'll see. Okay, the life L10 corresponds to reliability of 90%. So the way it goes, a lot of a number of bearings are tested to establish the dynamic load rating, and the life is declared, and if the experiment stopped when 10% of the bearings have failed. So that's 90% reliability. If we want to go higher reliability than 90% or 10% probability of failure, we need to make adjustments, and the coefficient life adjustment factor for reliability CR are listed here. So if you want to elevate from 90 to 99%, as you can see, this coefficient is 0.21. So essentially, you need to restate the life of the bearing as being only 21% of the life for the 90% reliability. And of course, they go hand in hand. So if you reduce the load, then the life increases, and if the life is too short to be satisfactory for the application, you want to go with a a size bearing that has a dynamic load rating high enough to with the adjustment for reliability to be acceptable. Okay. Bearing manufacturers, they have a lot of information on their websites and catalogs to assist with selection, including apps this time day and age to assist with selecting the bearings. But the basics remain. The theory is established, and this chapter is useful in itself. When you design with bearings, you need to account for a number of things. Firstly, how you assemble the everything together. If you look at this drawing here, which it has some flaws, and I'll discuss them. So the way things like being able to reach to where this retainer ring is, okay, being able to have the full assembly placed in together with the bearings and secure the bearings in place. There's no knowledge whether there's the possibility of disassembling the left side of the housing to where indeed you can insert from the left the full, the two gears on their shaft with the bearings readily assembled. So yeah, if I can remove this side, then I could insert the assembly from the left. Otherwise, my only possibility to insert it from the right, usually you press fit the inner race on the shaft. You'd have to do assembly of this large gear with the shaft in place. There's a key here. The pinion is large in size than this, the outer race diameter for the bearing to the right. So not very promising, really. So and then I'm listing here does not allow for thermal expansion. So I locate the bearing firstly on the shaft. I have the shoulder here, and then here I have there's a shoulder as well as a spacer. What appears this to be. The spacer actually could serve as also as a shoulder. But if this area, the whole shaft is temperature goes up, the bearings will force against the cap, which is secured with bolts or screws, not visible. But and then here you have a retainer ring, an external retainer ring, and thermal expansion is impeded. So you would like to secure one of the bearings and allow the other one to. So I could secure this bearing. It appears to be the bigger one, and also a candidate to take the thrust load. You cannot have both bearing take the thrust load. You select one. So you could locate the bigger bearings, allow have a cap, but don't force the cap against the outer race of the bearing in any way. Just allow some space for the outer race to slide relative to the housings. You solve the problem of thermal expansion. And also, if they are straight spur gears, thrust is negligible, but if they are helical gears, you would definitely consider the bigger bearing, the one that takes the thrust load. Okay, sometimes again helical gears, you can get the helix angle negative and positive here, and they could partially, if not fully, cancel each other's effect. Okay, but these appear to be gears, if not sprockets, for timing belts. Okay, so I said there are a number of things. How do you reach for? How do you assemble? Can you have access to removing a retainer ring that has to be placed at assembly? Engineers, when they do design work, they need to think of a lot of aspects before committing a design. It's really embarrassing to have all the parts fabricated. You want to put them together, and you overlook something. You cannot assemble your design. For locating, so here's the bearing at the end of the shaft. Here's the shoulder. Remember the radius here. That's the catalog information. You want to have the fillet radius on the shaft to be at most the fillet radius on the inner race, and likewise for the housing you need to consider the fillet radius of the outer race. Okay, so you locate the bearing using one of these nuts. It has 4 grooves and one of these washers, and this feature of the washer slides through a groove on the shaft. These are fine threads, and you adjust the tightness of this nut, and then you bend the aligning wing into the groove to locate or rather secure the nut against unthreading. Okay, and there are other designs. Studying existing mechanical drawings is the best way to learn how to design with bearings. Again, make sure you can assemble in a convenient way, and also make sure to allow for thermal expansion. Never consider having 3 bearings on the same shaft. There are some instances where you could. One is with taper roller bearings. So I've seen designs where there's a taper roller bearing on a loaded area of a bevel pinion that's overhanging, and then on the opposite end you have a cylindrical roller bearing that allows for thermal expansion. Okay, so taper roller bearings, you can assemble them on shafts like it's shown here. So the normal to the races intersects the axis of rotation of the shaft. Somehow, the 2 intersecting points are away from each other. If I mirror both bearings, okay, then these intersection line or the normals will intersect the axis of rotation towards the portion in between the bearings. So there's a reduction of the apparent length or distance between bearings by doing so. So as shown here, this is the O arrangement. If I mirror both bearings, I cannot mirror just one. I need to mirror both, because they need to I need a possibility of adjusting to near zero clearance the 2 bearings. So, but if I mirror both of them, I get what is called the X arrangement. The O arrangement is much stiffer in terms of angular stiffness. The X arrangement is less stiff because of the apparent reduction in distance between the reaction points. And you see them used the way it's said. So they are close to each other, are the X arrangement. They have some angular compliance, and on the opposite end you have a 3rd bearing. I've seen that with some automobile transmissions where the shaft was the bevel pinion shaft, the one that meshes with the ring gear on differential. Okay. When designing with thrust bearings, with taper roller bearings, they take thrust. the equivalent load, it's calculated with these equations. So you have one of the bearings taking the thrust. You need to decide which one. Sometimes these bearings could be at different sides. See the wheel, rear wheels of trucks, or the drum type rear wheels or in general wheels of automobiles. So you may have one bearing being bigger than the other one, but they are both thrust bearings. And you'd expect the bigger one to be the one that takes most of the or takes the thrust. Okay, so the equivalent radial load on the two bearings, you calculate them with this formula, and you have a table that gives you the some factors. The thrust factor and the dynamic load rating. Okay, and then there's a companion equation that takes the case of the load being over a stated limit in a sense similar to the early equations that we discussed for deep groove bearings. There are several paragraphs on installation and lubrication of bearings, as well as limiting speed. Also bearing stiffness, I think we discussed this. There are arrangements that have less compliance, angular compliance than others. Deep groove bearings, they can take some fractions of a degree of angular compliance versus the cylindrical roller bearings, which are very stiff angularly. The sealing problem, you want to keep contaminants out. They can be built in with the bearing. Bearings can be sealed on one side or both sides. They can be shielded on one side or on both sides. Sealing, meaning they're watertight. Shielded means there is a small gap, and you can lubricate with solid lubricant periodically the area behind the seal, or rather the shield, and grease drives out, excess grease drives out the impurities from the interface of the shield with the inner race. Okay, there's some information about the tolerances. This is the inch designation, or tolerances, and the use of lubricant. Could be liquid lubricant, or could be lubricant could be solid. There's petroleum jelly based. Okay. In terms of life prediction on the varying loads, you can have, for example, automotive transmission shafts support on bearings, and you can have the vehicle operating at the various speeds. You change speeds, whether it's manual or an automatic transmission, and in each speed the load will vary, the RPM of the shaft will vary. You would like to know what is the mean effective load, and mean effective loads, it's in essence an equivalent load in the equation to calculate the mean effective load observed by these two engineers is the one that's listed here. So they introduced new notations. P is actually K, exponent of the load lag relationship. P is either 3 or 10 over 3, that's 3.33. We have it introduced earlier as K. And then what is this equation? What do you see here? So Fi, individual load among the series of I loads. So say you you monitor how many minutes out of a 1 hour, say, use of the automobile, you drive it in a city and then on a highway. So what is the RPM and number of minutes of operation, which allows you to calculate number of revolutions at each of the loads Fi. Okay, so I have first gear. I know the torque transmitted. I know at what RPM I can calculate the first load, and then say it's a 5-speed manual transmission, I can calculate. There's more factors including, so you don't need to just limit of the speed, but also the instances of operation. Could be during acceleration, start from a stop, or cruising. Anyway, but you're assuming that this pattern is repeated the entire life of the assembly of the bearing as it's used for its application. Okay, so N, so we have the number of revolutions corresponding to this load, and then new load, new number of revolution, new node, new number of revolution. N is going to be total number of revolution in complete cycle. So it's going to be N1 plus N2. So you sum all these Ni's and it gets you N. Okay. And then we agree that this P should have been not introduced new, but already used. The early one was K, either 3 or 3.33. So here's listed what N is. Well, if it's to number of cycles, if it rotates at it says constant speed. This could also be defined in terms of really it's number of hours. So if the RPM is standard, then these could be replaced with minutes of operation, because you have minute here and minute here. And to calculate the cycles, you just multiply by the same number of RPM. But if the RPM is different, then you need to work directly with cycles, if it's making sense. So these two for constant RPM could be units of time. Otherwise, I need to convert using the different RPMs. So there will be an index for RPMs I, and I'm calculating corresponding NI. Based on the time recorded, okay, and you add all of them. Okay, so yeah, you just add number of cycles, all right, and so you calculate mean effective load using this equation, and then the life of the bearing would be, instead we had P. Or equivalent load was it earlier, the equivalent load P. Now use the FM, the mean effective load on the variable loads. And I guess this is it for this chapter. Again, if you're to do serious design work, studying the documentation of the manufacturer is always recommended, and I guess this is it. I'm going to stop here. Thank you for watching.